Let's now talk about do a summary of the properties of a conductor, of the things that we have discussed and some other consequences of them. So the first property is that we figure out that the electric field is zero inside a conductor. From this property, we obtain the result that the electric potential inside of a conductor is constant, and it's the same on the surface of the conductor. Same on the surface, the same inside. The third property is that since the surface of a conductor is an equipotential, it has equal values of the electric potential, that implies that the electric field at the surface of the conductor must be perpendicular to it. We know that it is a general result that an electric field would always be perpendicular to the equipotential that passes to the point where the electric field is evaluated. So this implies the perpendicularity between the electric field and the surface of any conductor, charged or not charged. The fourth property is that, derived from the previous one, is that the equipotentials near a conductor, they must have the same shape, very similar shape to the surface of the conductor. Because the surface is an equipotential, the electric field at the surface is perpendicular to it, and the electric field is not going to change very much if you are close to the surface. It will still be pointing pretty much in the same direction as on the surface. Therefore, the equipotential near the surface should have the same shape as the surface. Let me illustrate that these last two properties. Since the conductor has a value of the potential that is constant everywhere, particularly is constant on the surface, the electric field at the surface must be perpendicular to it. The other property is that if you draw equipotentials near a conductor, the equipotentials are going to have the same shape as the surface of the conductor. The reason being that they must also be perpendicular to the electric field, and the electric field at this point and the electric field at this point are not going to change very much. They would still pretty much point in the same direction. So the shape of the conductor is preserved on the equipotentials near the conductor. This also tells you that if you have two conductors near each other with different shapes, the equipotentials near this rod, for example, will have the shape of a rod. The equipotentials near this other conductor will have the shape of that conductor. And as you move away from each object, the equipotentials will kind of the shape of the equipotentials will change into the other. It will transform from one into the other. Let's look at the potential of a charged metal sphere. So this is your charged metal sphere. Since it is made of metal, we know that the electric field inside is zero. And if we put a charge on it, that doesn't change the fact that the electric field is zero. But then there will be a potential outside of the sphere that, as we know, will be equal to the potential of a point charge. So if you were to draw a plot of the potential versus position, or potential versus distance from the center of the sphere, then if r is bigger than the radius of the sphere, that is a, so in that region where r is bigger than a, the potential as a function of r decays as 1 over r. But if you plot the potential in the region inside the conductor, then it must be a constant. It must be a straight line with slope 0. And the value that it has will have to be equal to the potential on the surface, kq divided by a. So outside the potential behaves like kq or r, inside the potential is constant and equal to the potential on the surface. from the expression that the potential on the surface is kq over A, you can see that kq is the potential on the surface times A. So in general, you can write an expression for the potential outside of the sphere in terms of the potential on the surface of the sphere. That can be useful sometimes. So the potential outside can be written as V surface times A divided by A. Let's work on a conceptual question here about two spheres connected by a wire. One of the spheres has a charge of 2 nanocoulombs. The other sphere has a radius of 2 centimeters. R1 is 1 centimeter. And the question is, what is the charge on the second sphere? How do we calculate that charge? So this is the statement of the problem. We're going to use the ideas we have already discussed for a conductor to solve this problem. Both the spheres and the wires are conductors, and once they're connected, they form a single conductor. For a conductor, no matter what shape it has, it is true that the potential everywhere on that conductor is a constant number. So that means that the potential on the surface of sphere 1 should be equal to the potential on the surface of sphere 2. So if you can use this to calculate what is the charge on the sphere number 2. So using the property that I just mentioned, that the potential everywhere on the conductor must be constant, then and this is basically due to the wire connecting the two spheres. The wire guarantees that the two potentials on the sphere will be the same. Then we can write the equation that V1 equals V2. That is, the potential on the surface of sphere 1 should be equal to the potential on the surface of sphere 2. I'm going to model the potential on sphere 2 as kq over r. The same for sphere number 2. So we're basically assuming that the spheres are far enough from each other that each sphere will have a spherically symmetric distribution of charge, which allows us to use that the potential is kq over r. So making those two expressions equal to each other, we have that the charge on the second sphere should be equal to the ratio of the two radius of the spheres multiplied by q1. So placing the numbers, radius number 2 is 2 centimeters, radius number 1 is 1 centimeter, the charge of sphere 1 is 2 nanocoulombs. That gives you 4 nanocoulombs for the charge on sphere number 2. So the sphere with the biggest radius will have to have the biggest charge to compensate for that, since Q1 over R1 should be equal to Q2 over R2. Otherwise, they wouldn't have the same potential. And the system would not be in equilibrium if the two potentials were different. You would produce a current through the wire which will equalize the two potentials. So at the equilibrium condition guarantees that the potential everywhere is going to be a constant, which is the property that we're using here to find the charge, the unknown charge. Let's talk about a property called capacitance, which is defined for a device that is made of two conducting plates, one with negative charge, some area A, and one with positive charge, also area A. They're identical to each other, and there is a distance between them. So every time we talk about two metal plates, In the context of electricity and magnetism, we will be referring to those plates as a capacitor with a quantity called capacitance, which we're going to define next. So the difference in the potential of those two plates is given by the electric field between the plates multiplied by the distance between them. The electric field for a capacitor, we know that is eta, the surface charge density, divided by epsilon 0. That gives you that the difference in potential between the two plates is equal to eta divided by epsilon 0 times d. Now eta is the surface charge density, so it's Q divided by A multiplied by d and epsilon 0. So if we solve for Q, if we write this expression for Q, we get that Q is proportional to the difference in potential, and the proportionality constant is A epsilon 0 divided by d. A and d are properties of the plates, of the capacitor itself. Epsilon 0 is a constant of nature. So the physical properties of this capacitor determine how much charge it can hold at a given difference in potential. So if you compare two capacitors that have, if you connect two capacitors, one big, one small, to a battery, 1.5 watt battery, the biggest capacitor, the one that has the biggest A and the smallest distance between the plates, will be the one that can hold the biggest amount of charge. So that proportionality constant, which has to do with the dimensions of the device, of the capacitor, is what we denote with the letter C, and we call that the capacitance of this capacitor. And the expression A epsilon 0 over d applies to the capacitance of a capacitor that has parallel plates. The plates are flat and they're parallel to each other. If that's the case, then that is the expression for the capacitance. So the name capacitance is clearly coming from the fact that it has to do with the capacity of this device to hold charge. For a given delta V, C tells you how much charge this device can hold.